Okay, hi everyone, welcome back to the second lecture of the deep learning class. We are picking up where we left off, and we will today start looking at image classification, supervised learning, and meet our first algorithm, which is almost not even a real algorithm. It's just sort of to get started. Okay, so let's get started. The plan for today is we'll pick our first toy problem, the entry-level problem that we want to study. We will give you a supervised learning view of that problem, and we will introduce our first, classifier. And next time we will start looking at linear classifiers, and then ultimately build towards neural networks. I see a comment saying using the link on the class webpage, the one. Oh, I see. Apparently, the link on the class webpage for Piazza is the more accurate one. The one on Canvas doesn't work. Thank you for commenting that. Okay, so let's get started with image classification. So this is going to be, just the entry level problem that we will look at. I apologize. For some reason, I'm seeing that my own slides in the broadcast seem to be a couple of seconds behind me, but I'll continue, and hopefully it catches up. The slides catch up. Okay, so image classification is a core task in computer vision. It is going to serve as our test bed for developing a lot of the ideas that we want to develop. It is a simple enough problem, but captures enough complexity. You are given an input image. You're given a list of categories that are of interest, and you're asked to tag whether or not one of these categories is present in this image. We could pose this as multi-label classification, meaning that for each of the categories you could say yes or no, but for simplicity we will just assume that there's one of those categories present, and so you just have to pick one of those categories out. You do not have to say yes, no. So this is a multi-class classification problem, right? This is pretty simple. The reason why this task is difficult is because the way humans perceive images is very different than how we represent them in computers or for programs. You and I aren't even aware of these objects called pixels, but the way images are represented in computers is by arrays. So if you've taken a computer vision class, you know there is a height by width by 3 tensor. That is how images are represented, where each pixel in this tensor corresponds to intensity if it's a grayscale image, or RGB values if it's a color image at that particular pixel. So this number says 871, and this other number says 821, but that's how together they form this image. This is not how humans think of the visual world. The problem with this representation is that it is very difficult to go from, the task that we're setting up for computers, for machine learning, is to take in this list of numbers and to output one of the classes. And this list of numbers undergoes massive amounts of variation depending on how that picture was taken. So if the camera viewpoint changes, if we start looking at this object from another viewpoint, those numbers undergo massive amounts of changes. Humans don't actually notice all that much when we sort of, move our head, we look at an object from another viewpoint, we don't notice significant changes, but the numbers in the arrays are significantly different to the point that they almost become unrecognizable. There are also problems with illumination. So objects can be lit from different directions. This appears to be lit from top, this appears to be lit from side, this appears to be lit from top again, and this makes significant differences to the lighting and the intensity of the pixels that we end up looking at. So the pixels will appear bright or dark depending on what the lighting conditions were when this picture was taken. You and I don't really notice that, but that changes the intensity values at those colors. Objects also deform. So these are not rigid bodies, the objects that we will study, cats in particular, can take arbitrary shapes, so they look very different in different images. Of course, there's the problem of occlusion. What we often find is, look at this image. There is just this one little tail hanging out of the couch. And most parts of the object are actually missing. You just have to hallucinate the fact that yes, that there is an object under the cushion buried there. But the evidence in this picture is just a small amount of pixels from which you have to identify that there's actually that object in this picture. And of course, there may be background clutter, so it may be very difficult to know what are the delineating regions between an object and a background. But we still have to identify that object is present in this image. So here's the API of an image classifier, if you will. What does an image classification program look like? It's basically a function that takes in an image and returns a class label, and you have to do something in between to go from images to labels. And the weird thing that machine learning and deep learning as a consequence will advocate is that we will write this program not as an implementation of a particular algorithm, but through a completely different paradigm, because we simply don't know what is the algorithm that goes from a list of numbers to a category label. Nobody knows what that algorithm is, and so and people have made attempts at that. People have said, maybe there are certain objects that have certain kinds of boundaries. So maybe if we first do edge detection in those images, find certain shapes or kinds of corners, and if enough of them, and start counting, maybe when this kind of corner happens and this kind of corner happens, if enough of them are happening, then we will call it a particular category. So these kinds of attempts have been made, but largely these attempts have not been very successful. What has been successful is the data-driven approach of machine learning, which is to say, I don't know how to write this program that goes from images to class labels. So I will offload that burden to a algorithm, to another algorithm, or to a computer. So all I will ask you is for a data set of images and class labels. I will use something called machine learning to give me a model to train a classifier, and then I will evaluate that classifier on new images. And over time, my performance will improve as you give me more data. If you compare this, if you're a classical sort of algorithms person taking a CS class in algorithms, and I were to come to you and say, the way we're going to sort numbers is not through bubble sort or quick sort, but the way we're going to sort a list of numbers is we will ask our users to give us unsorted lists and sorted lists, give us some data set. Then we will go tinker with our machine learning algorithm, and then we will come back and give you a sorting. And initially the sorting will be wrong, but over time, as you give us more data, our sorting algorithm will get better. If you told me that, classical CS people would find that not only shocking, but laugh at that suggestion. We do not learn to multiply numbers by saying, hey, the product of 2 and 3, how about 5.5? No, we're slightly off. Okay, how about 6.5? No, still off? Okay, we're learning, we're getting better. But the reason why we do this in machine learning is there simply is no known algorithm to go from to solve the kinds of problems we want to solve. And this appears to be a fairly general technique. If we can just collect a data set, we can write a general purpose machinery here in the middle. We can apply this to new domains. Because ultimately then the images may come from very different domains. They may not be of cats and dogs. They may be of medical imaging, aerial imaging, and we'll be able to swap problems in and out, but still use the same underlying machinery. Okay. Just a quick note on notation that you will see me follow in this class. So I will often use small letters XYZ for scalars. I will often use, for vectors, I will use this notation where I will draw a little arrow on the character that I'm interested in. If this was LaTeX, then I would just use bold X or bold Y, but we do not have that luxury, so I'll just use the vector notation or the arrow notation on top. By capital, I will use capital letters to either denote matrices or random variables or sets. We will typically use small d to denote input dimension, and this will come up. This will be our usual notation for this, and you'll usually see this show up as x belongs to r to the d. Usually the output dimension or number of classes, I will typically use k, so you might see me say, y belongs to r to the k. If this is a regression problem, y will typically be my output variable, x will typically be my input variable. Usually the number of samples in a data set, I will use small n or capital N, and the parameters of a model, you will typically see me use either w or theta for parameters. And so that's the usual notation that you will see me use. So armed with that notation, let's take a look at what is supervised learning. So this is, the first entire module of our, first maybe 2/3 of our semester will be spent with supervised learning. We'll spend some time in reinforcement learning and also unsupervised learning. But let's revise ourselves, refresh our memories about what supervised learning is. And so this is all of supervised learning on a slide, right? Here's what we're going to do. We are given some input X. This input may be a scalar input, or it may be a vector input that lies in some D dimension, or if these are images, they may be height by width by 3 type images. We can also have text. We can, or text of a particular kind represented in some other feature space. But we're given some input X. We are given, there is some output Y. Maybe we want to label images as cats versus dogs or some categories. We want to label emails as spam versus not. Maybe this output space is -1 +1. Maybe we're trying to do binary classification, or maybe the output space is 1 through k. There's some k discrete categories that we're trying to label this with, or maybe the output space is in some continuous r to the k. This is a regression problem. Doesn't matter. There is some input, there is some output. And what we are going to do is there is some unknown target function. There is some function that maps from the space of X to the space of Y, and this is the true mapping. This is reality. We do not have access to reality. We do not know what generated the data. We do not have access to F. We only have access to a data set, a set of points, D, which is a collection of pairs of X and Y, where Y are basically F evaluated at X. So X1, F of X1, X2, F of X2, and so on. So we're given evaluations of F. We are not told what F is. From this data set, all of supervised learning resolves to 2 goals. You can have 2 different goals that you can ask for. You can say, my goal can be find F. So find me this function that generated these XY pairs, or that generated this mapping from X to Y. Or your other goal can be to predict F of X at new X. So at new data points that are different from your data set, use this data set that I've already observed to predict F at these new data points. Notice that these are related but subtly different, importantly different goals. These are actually, sometimes we'll be able to do both, but these goals can sometimes be in complete conflict. The goal of being able to predict f of x at new x does not involve being able to create these functions f that have any meaning. It could be that, large parts of deep learning is going to be that f is maybe some black box that is not very intuitive. We don't know whether f corresponds to something meaningful in any sense. There are problem domains where you do not get to choose black box, where I actually care about what is this function. Biological data, genomics, astronomical data, anytime you're trying to do science and where you're trying to discover what is this underlying phenomena, and I'm interested in what that underlying phenomena is, and all I have is samples, you actually care what f is. In a lot of applications, we won't care what f is. We'll just want to use it for new examples. So we'll have to be clear about what our goal is. Maybe in image classification, we actually don't care how humans perform image classification. We just care that I have a black box so that I can perform image classification on new images with. Okay. I hear a question on BlueJeans. Is it an issue if the target function is stochastic? No, it's actually not an issue. We will typically model that by saying that y is a random variable, or f is some deterministic function of x plus some noise, or has some stochasticity. It's not going to be a problem. Okay, so that's the goal of supervised learning. And so how do we approach this problem? How do we solve this problem? And so here's the recipe for all of supervised learning. This is going to be all of supervised learning in one slide. The recipe is: step one, you define something called a model class. Or if you have taken a machine learning class before, they may have also called this a hypothesis set or a hypothesis space. And what this is that you define a set of mappings from x to y, capital Y. So h is a function that maps from the space of inputs to the space of outputs. And so if we want to evaluate y, we just make a call to h at some x, and we get this value. And maybe it's some parametric function, maybe it's some non-parametric function, but the space of all such functions or some restricted space, that's your model class. This could be a neural network, this could be a linear classifier, this could be a non-parametric model, this could be anything. But you define, as a designer of an algorithm, a model class or a hypothesis space. And this is where a lot of in deep learning land, you have sort of neural networks come in, designing neural networks. The second thing that you do is you define something called a loss function. How poorly am I doing if I pick this particular edge? The loss of h, a particular function in this family, given this data set, and it may typically factorize over your data set. So it may be L sub I of h, comma, let me actually just erase that a second. And write that as h of xi, comma, yi. Okay, so for the ith example, the real label in our data set was yi. You predicted h of xi. How good or bad is that prediction? The target label said cat. You predicted dog. How good is that? And that may change per example as well. That's why I indexed L sub I. And then I just sum that up over all example and take an average over my data set. That's just, different applications may have different loss functions defined. That's step number two. And step number three, all of supervised learning is basically search or optimization in the model class, where MC is model class. So all of learning is the search for an H star, which is argmin of H in our hypothesis class that minimizes the loss between H and this data set T. That's it. This is all of supervised learning. You can spend semesters taking entire classes on it, but this is all of that summarized in one slide. And ultimately, it boils down to three components in learning. The component number one is defining of this hypothesis class. You typically do not want to allow all possible functions from X to Y. That would be too many. That does not work too well. And so designing neural network architectures is about defining this model class. You want to define reasonable loss functions that maybe prioritize certain kinds of parameters or certain kinds of members of your loss functions. Maybe you care about certain kinds of predictions. Maybe you care less about other kinds of predictions. And all of this argmin is, optimization or search. This is going to be issues of gradient descent, or do I use Adam, or do I use something else? That's going to be concerned with the argmin part. Those are the three components of supervised learning: model construction, loss construction, and minimization. And once we can figure that out, we have all the pieces together. Okay, so yep, exactly what I wrote down. We have some model class. Learning is search in the model class. So why aren't we done? Why are we still, studying this problem? Why is this an active research area? And let's just study that by an example. Here is a particular example. I have four input variables: x1, x2, x3, x4. They are binary or Boolean, meaning that they take values 0 and 1. So there's four of them. 2 to the 4 is 16. So there's 16 possible rows here. I've given you 7 rows out of the 16 possible. And this is the function y that I'd like to f. So the y values. So the function f, which is unknown, that I'd like to learn. And here are their values: 0, 0, 1, 1, 0, 0, 0. And maybe I come to you and I say, okay, for x1, x2, x3, x4, when I do 0, 1, 1, 1, can you predict y for me, and so on. So it's a simple simple game, and we can play this game where I can come to you and say, hey, what do you think the set of rules is? What do you think f is the underlying function, and therefore what do you think should the prediction be at this point? And I'll pause there for a second to see if people have thoughts on what is let's try to come up with a simple rule that if you people from ECE or electrical engineering backgrounds typically are good at this sort of stuff, coming up with Boolean functions that go from X to Y. I'll give you a hint. There are 2 rows that have 1s in it. This fourth feature seems to be 1, and the second feature seems to be 0 for them. And so one guess you might make is that this rule F is basically that x4 and naught of x2. Maybe that's what this function is. So you might want to predict a particular value for it. But if you played this game with me, where you made a prediction, and then I had to fill in another row, it's pretty clear that you will, yep, I'm seeing people make guesses of x4 and not x2, also x4 and x1 plus x3, and there are multiple things. But if you played this game with me, and I was an adversary, I would just look at your prediction and choose a y value that was different from your prediction. So you'd be wrong. And so let's ask ourselves the question, how many times can you possibly be wrong if I keep picking new rows? So remember, our hypothesis class was, the set of functions h that map from x to y. So let's ask, how many functions are there that map from, if there were, instead of 4, if there were d Boolean variables, so if d Boolean x's, and 1 Boolean output, How many functions are there? How many functions are there with D input variables and 1 output variable? I'll give it a second while people think about this and maybe type in the event chat. 2 to the 2 to the D minus N. There is still that many functions, number of functions compatible with dataset. That's how many functions are still compatible, meaning that they agree on these n rows, but potentially disagree somewhere else. And that's how many ways there are to lose that game with me, where if I kept pulling out another row and I kept asking you, do you think a 0 or a 1 goes here? You would keep losing. And so this is a fairly long time. N has to be very long. There are applications where D is so large, it's actually much larger than N. That 2 to the D is nearly always going to be larger than N. The idea that 2 to the D is smaller than N is usually never the case, which means that we're always on the losing side. So how can we ever hope to generalize and put entries in this row that are in new examples? So learning is hard, and without any assumptions. So if you don't make any assumptions, there is just no learning. You cannot allow for empty rows where arbitrary things can be put in. If you don't make any assumptions, then we simply just can't learn. Okay, so here's going to be the procedural view of learning. And the procedural view of learning is that there is a training stage and a testing stage. And during the training stage, we take the data set of xi's and yi's, and we produce a model h, or a function from our hypothesis class. And during the testing stage, we just apply h to new data that comes in, and we evaluate error. This is the procedural view. The statistical estimation view of learning is that our variables x and y are random variables, and what we observe in our data set are samples from some underlying distribution, p of x comma y. We do not know what this distribution is, but we just see samples from it. And when we perform learning, we are actually learning something about this unknown distribution, p of x comma y. And therefore, when we apply on some new examples that are also coming from the same distribution p, we have some hope of generalizing to this test set. So that's the statistical estimation view of things. Here is a particular breakdown typically of errors, and this is what I call the classical learning theory view of things. And I will also mention later this view breaking down, but it's a good conceptualization of why things may fail in a machine learning model. And this is good to keep in mind when things don't work, as to why are things not working. And so let's look at error decomposition. So I'm plotting on this space a point, and that point is a particular function. That's reality. That's the mapping from this x to this y. The problem in this slide is slightly different. It's not image classification. We're also annotating pixels with what categories they are, but essentially the task is still the same. We haven't changed the intrinsic issue here, that this is all a mapping from an x to y. What we are going to do is, here's your illustration of a model class. So a model class in the context of deep learning is that you have chosen an architecture, let's say AlexNet or VGG or something. That architecture has some layers. Don't worry about the details. We will teach you these details in the upcoming class. But this is a set. Every point in this set corresponds to some setting of parameters. You have to choose the filters, the normalization weights, and everything that of the entire architecture. So every point in this set is one setting of all parameters, and you can have lots of different continuous parameters, and that's why this is the model class. This is a parametric model class. The immediate thing that you realize, that reality is not inside your model class. It may not necessarily be the case that this function mapping x to y can actually be represented by some setting of parameters in this space of functions, right? So almost immediately you realize that there is something called modeling error or approximation error. It's called both modeling error and approximation error, which is what is the best model in our model class, best in terms of how close can it get to reality in terms of our model class. So we are off the bat, before we've done any learning, we have to pay that penalty. We have to pay the penalty of just as soon as you choose a particular architecture in neural networks, you have to pay this cost. But this is actually not the only source of error. The other source of error that happens is known as estimation error. When you learn from a data set D, you will not find the best model in your model class. You will actually find something else, this other point. And the reason is that D is not an infinite size data set. It is a finite data set. D is itself a sample from the true distribution P, right? So since D is sampled from P of X, Y, if you had chosen another sample, maybe you find out some other model in this model class. Maybe if you choose a third sample, you find somewhere else. So this distance between the best you can do and what you actually accomplish with D, that's estimation error. And that is not the only source of error either. There is actually a third error, which is optimization error. So between the best you could do given this data set and what you actually find, the difference is optimization error, because we cannot actually minimize the loss to 0 or to even the global optimum of L. The loss functions that we're going to be working with are non-convex. Maybe we will do approximate optimization, and maybe we'll do early stopping. So wherever we actually end up is going to be different from where we could have ended up if we had optimized to optimality. So those are the three sources of error. We made mistakes as soon as we chose a model class. We don't learn on full data sets and on infinite data sets, and we have optimization error. You can tweak certain design choices to change these things. You can, for example, make your model class smaller by choosing simpler functions. So if you, for example, make your neural network shallower, have fewer layers to the point that it's just a linear classifier, a multi-class logistic regression, your modeling error will go up because you just reduced. You went down from this bigger set to a smaller set. Your modeling error went up. You went farther away from reality, but you have fewer parameters to model. And so your estimation error will typically go down. Your estimation error will go down, modeling error went up, and your optimization error in this case dropped to 0. Linear classifiers with certain types of losses, like with cross entropy, that will get you, that can be solved to global optimality with gradient descent. And so optimization error for those will be 0. On the other hand, you can expand your model class. So you can choose a different architecture, VGG19, ResNet 50, ResNet 1000, whatever. You can make these architectures much deeper, which will expand your model class. In some case, your model classes will even be nested. They will contain other model classes as special case. And so in this case, your modeling error is much lower. Maybe you are able to come up with a theorem that says every function from X to Y lies in my model class. I can represent every single function. So modeling error is 0. But so what? That's not the only source of error. Typically, if your model class is large, you have a lot of parameters, you will need a lot more data to estimate those parameters. So for a given data set size, your estimation error will go up when you increase your model class. When you have more functions in your model class, you will need more data points to search for those functions. And so your estimation error will go up. And classical learning theory says that your optimization error will also go up. And so this is why there are trade-offs. Do you want more expressive models? Something can happen to modeling error. Do you want less expressive models? Something can happen to estimation error, and so on. So to summarize this part, approximation or modeling error is just the error out of the gate. You approximated reality with a model class, therefore you have to pay that error. Estimation error is that you're trying to learn that model with finite data as opposed to infinite data. And so you have to pay that error. Optimization error is you were either you were lazy and maybe you couldn't or didn't optimize to completion. Maybe the problem you're trying to optimize is NP hard. Maybe you can't optimize it to completion, and that is optimization error. There's a source of error that we didn't mention, but some of the comments did, which is known as Bayes error, that maybe the reality is just harsh. Maybe the function you're trying to learn is stochastic. So even with the perfect model of it, when you make a prediction, sometimes you're right, sometimes you're wrong. Reality just sucks, and so you're going to have that source of error. It is good to keep these sources of error in mind, because when things don't work, you can ask, what is going on? Is my model class too expressive? It is less expressive? What should happen to these different sources of errors? And we'll talk about these in later lectures as well. One caveat I want to say is that a number of recent empirical results in deep learning question our intuitions built from this clean separation. So, for example, there are recent results in deep learning on a phenomenon known as double descent. There are results on, we know, for example, in deep learning, we've seen empirical evidence that larger model classes can actually be easier to train and may actually generalize better as well. So empirically, we've observed that optimization error does not seem to go up as you add more layers. Some models actually get easier to optimize as they have more model classes, as they have a bigger model class. So there's a caveat here. This clean separation does not explain everything that we are seeing in recent results. Okay, so with that, let's move to our first classifier. Let's meet our first classifier. These are things that you should be familiar with, but this is a refresher. This is the nearest neighbor classifier is so simple that it's basically shouldn't even be a classifier of a kind. It is a model that says, I will do no learning, I will just memorize everything. So the training function, which is supposed to return a model in some model class, just memorizes all of the training data, just keeps it around, does nothing, and returns that. And the prediction basically predicts the label of the most similar training image. So the model is the entire data set. And how do you do this prediction? You just find the closest, the most similar training image and predict its label. Copying, basically. When you don't know, you just copy. You find similar situations and you just copy. We're going to see, we're going to be using a running example of CFAR10, which is a data set, a very popular data set in computer vision. It has 10 classes. It has 50,000 training images and 10,000 testing images. These are the 10 categories. You will use this in your homework as well. These are low resolution, 32 by 32 images. They allow you to do easy testing of your ideas. And so these are some of the training images. And let me show you, here are some testing images and their nearest neighbors. And these rows are sorted by distance to this example. So the first image is the closest, the second is the farthest away, the further away, and so on. And we notice that, we can kind of get neighbors that look similar, that have the same sort of outline. They're not identical because it's not that the same image is present in train and test, but they're sort of holistically similar. There is a blob in the center with white stuff in the background. We'll see similar things like that in the test images as well. And so then we can just copy over labels from these nearest neighbors. And more generally, there are basically 4 things. These things are, nearest neighbors are special cases of something known as an instance-based or a memory-based classifiers or learners. And there are 4 things that you can specify. And as soon as you specify them, you get one instantiation of a learning or a memory-based learner. You have to specify a distance metric. How are you going to compare distance between xi and xj? And how many nearest neighbors are we going to look at? Are we going to perform any weighting between the different nearest neighbors? And how are we going to fit the local? How are we going to fit with these neighbors? How are we going to make an actual prediction? And so the one nearest neighbor algorithm is the simplest instantiation of this idea, where the distance metric is something like Euclidean. I'm just going to do Euclidean distance or L1 distance or something simple like that. I'm only going to look at the closest data point. So it's in the name, and there's only one nearest neighbor. There's only one neighbor that we are polling, so there's no weighting needed. And we're just going to predict the same output as the nearest neighbor. So it's just a copy of the neighbors. And this can be easily generalized to a k nearest neighbor algorithm, where the distance function stays the same. You, instead of one, pick k neighbors, don't use any sort of weighting function, but just predict the average output amongst the nearest neighbors. So you can do majority vote if it's labels, or if you're doing regression, you can just predict the average value, y value of the x's that are the nearest to this particular data point x, that test point that you want to predict for. These things, as I mentioned, can also be done for regression. So this is a visualization of one nearest neighbor for regression, where x, if our x is a one-dimensional variable and our y is also a one-dimensional variable, and this is our training data set of xi, yi pairs. This is a one nearest neighbor with a particular distance metric, where as long as we are at these x values, as long as this is our x1, this is our x2 in our data set, this is our x3. As long as we are close to x1, we basically keep copying the y1 value. So this is y1, for example. When we become close to x2, we copy the y2 value. When we become close to x3, we copy the y3 value, and so on. For images, you can use what is known as L1 distance. So for each pixel, we're just going to train. This is a training image. This is an array showing intensity, or there can also be tensors with RG and B. But for each of those channels, we're just going to compare pixel differences and take absolute value and just add them up across pixels, which is just an pixel-wise absolute value differences, which is an instantiation of just L1 distance between these two tensors. You can also have L2 distances, and ultimately these things are just going to be design choices. These are the hyperparameters that we're going to talk about how to pick. And so this is. Sorry, I just noticed a comment that says it would be helpful to have slides beforehand. Sure, we can do that. I think we can look into that, and that'll make it easier for people to follow along. Implementing a nearest neighbor classifier is fairly easy. This is a particular implementation on the slides. It's basically two functions. You notice that the training function does nothing. It just keeps pointers around or just makes a copy. So X is memorized, Y is memorized. So, training is trivial. Prediction just requires computing distances between the testing points to the training points, and then just keeping the indices and returning the indices of that. So these are very simple things to implement, which is just copy the closest the label of the nearest training image. You can obviously ask questions like, with n examples, how fast are training and prediction? Do we expect with n examples training to take order n time? Do we expect it to take order 1 time? Do we expect prediction to take order n time or order 1 time? I'll pause here for a second and see if people have thoughts on how fast training should be in terms of complexity and how fast prediction should be. Training is in fact O1, prediction is ON, and that's actually a bad thing. It's actually an inverse of the kind of behavior that we'd want. Training is typically something that happens offline. Prediction is something that happens lots of times. I train a model, I deploy it, and I expect the deployed model to operate quickly. And this is the opposite. Nearest neighbor has the opposite behavior of what I want. Training, I can afford to spend some time on. It is typically testing that I want very fast. Okay. Let's move on. There is a demo that I've linked to here. I encourage you to play with this. It'll give you intuitions for how these things look and what the decision boundaries look. But in the interest of time, I'll move on and not engage with that. One particular question that it's a typical question. And by the way, I'll take a moment here to. So the question is, what is the best value of k? What is the best distance to use? And a very common joke in machine learning is that if you ever fall asleep in a machine learning talk, and then are woken up at the end and have to come up with a question on the spot. And I'm not saying this happens to full professors, but let's just say it's not unheard of. Maybe you're the host and you fell asleep in a talk, and now you have to ask one question about a machine learning talk. That one question typically is, how do you pick k? Because in any machine learning talk, there is going to be some parameter or a hyperparameter called k, and you can always ask, well, how do you pick k? And if you have fallen asleep giving your talk and you have no memory, the answer to any question like how do you pick k is typically cross-validation. And so that's what we're going to teach you today, that how do you pick k in nearest neighbors and how do you pick distance functions. These are things that are called hyperparameters. They're called hyperparameters to distinguish them from regular parameters. By parameters, we typically use that word to refer to the parametric family of H. Maybe H is indexed by some parameters W. K and distance are not directly controlling H. They are indirectly controlling H, and they're controlling your learning algorithm. And so these are typically called hyperparameters that control how you learn rather than what functions you learn, rather than directly controlling the functions. And this is typically very problem dependent. And we're just going to see what works best. And the way to do this is you have a few different choices. You can, you have a data set, you can choose hyperparameters that work well on the entire data. The problem with this is that k equals 1 will always work well on the training data set, because if you find neighbors from the training set and also make predictions on the training set, each data point is going to find itself and therefore copy its own label, and you will get always zero training error. And so yeah, it will appear like k equals 1 is the perfect thing to do, but it's obviously not in all situations. The other idea is that you can split your data set into train and test. And always, choose the hyperparameters that work best on test. This is definitely a bad idea because, we are not allowed to test our test set. The idea of a test set is that it is supposed to tell us how well our algorithm does in the wild. If you do anything to optimize performance on the test set, then you have broken its sole job, which is to tell you how well you're going to do on new data. In supervised learning and machine learning in general, supervised learning in particular, we are always concerned about how well we will perform on new data. We do not care about how well we perform on data we have already seen. And so this is a particularly bad idea. The approach that does work well is something known as, validation. So we will break our data set into 3 parts: a train part, a validation part, and a test part. We will, depending on the classifier you have, you will train your classifier on train. Nearest neighbor doesn't need any training. It'll just memorize the training set. You will pick hyperparameters on val. So for example, you will pick k star and d star, which is the optimal distances, which minimize, or maximize accuracy on val. And then you will use these k stars and d stars to compute accuracy of your model on test. And that way your test set is doing just one thing, giving you an evaluation, and you're not performing any optimization on the test set. Therefore, it is telling you how well your algorithm might perform on new data. When your data sets are small, you may not want to break out your data set into like an 80 or a 60-20-20 split of train, val, and test, you may not have as much data. So a common idea is to break out a test set and on the training set perform what is known as cross validation. That is to break it up into folds, maybe 5 folds or splits of your data. Treat one of those splits as the validation one. So maybe fold 5 is the validation, and you train on these 4, find the best K setting on this fold and report on test, and so on. And so you can repeat on all of these all of these splits, and this allows you, and then you average the performance, and this is known as cross validation. And this allows you to overcome the fact that you may not have a lot of data to carve out a big portion of validation. And typically you will plot functions like these. So for K, you will vary K from 0 to whatever, some large value. Your cross validation accuracy is giving you the accuracy on the validation fold. And so for each setting of K, you notice that there are multiple points here. This was 5-fold cross validation. So therefore you have 5 points on this plot because we were measuring accuracy on the validation fold. Averaging them tells us how well the cross-validation number, and generally looking at this plot, it seems like K equals 7 works well for this data set, and that's what we'll use on the test set. Okay. One quick comment I want to make is the distinction between parametric and non-parametric models. So when I initially gave you an intuition early on about supervised learning, I said, there's a hypothesis class which maps from X to Y, and I said maybe H can be H of X can be something like W transpose X, and H can be, for example, indexed by a parameter W. This intuition is valid for parametric models, but there are models that do not have any explicit references to parameters. And the way to think about them is this particular question. The question is, does your model class, sorry, I'm just trying to find eraser so I can remove this. Yeah. So does your model class grow with the amount of training data? If the answer is yes, then you're looking at non-parametric models, and if the answer is no, you're looking at parametric models. And notice, picture that function, the model class that we drew, H. Does the size of this set grow with the amount of training data? In a neural network, every member of this set is a setting of parameters of all the layers. Whether you have 1 data point or you have 10 data points doesn't really matter. The size of my set is fixed. As soon as I choose an architecture, I have chosen the size of my model class. But in nearest neighbor, the complexity of the decision boundary and the kinds of functions that you can learn change depending on how many data points you have. If you only have 2 data points and you're using L2 distance, then you can just learn a linear classifier between them. But as soon as you have 3 data points, you can learn non-linear decision boundaries. And that right there tells us that nearest neighbor is a non-parametric model. And that's good to keep in mind. Okay, one quick thing, side detour about nearest neighbor. So this is a really cool piece of work that our own James Hayes, Professor James Hayes, who teaches the computer vision class, he's a faculty member in ICT, he did back when he was a grad student at CMU with Alyosha Efros. I was also around in grad school at the same time, and it was so much fun listening to James's talk when this work came out. This is a piece of work called scene completion. It really just demonstrated how powerful nearest neighbor methods were. And what they did was that they used nearest neighbor techniques for infilling regions in images and replacing them with other regions. And so what they did was they started with a large collection of images, script from the web. They given a particular image and a hole that you want to fill in this image, they performed nearest neighbor in a feature space known as GIST, but those details don't really matter. If you're taking computer vision class, you'll learn about this in a vision class. Here are the top 200 nearest neighbors to this particular image in some GIST space. And then what you do is you basically do some slight context matching about aligning these images, and then you can basically copy over content from the nearest images, do some Poisson blending, and actually get just filled in versions of these images. Voila, you've taken parts of the image and you've replaced them with parts of another image. This is a really, really powerful and compelling demonstration of nearest neighbors beyond just the simple classification or regression settings that this had been used for. So here's an image. We don't like this facade. We crop that out and we fill it in with something else. And these results are so cool. Let me go back and forth. You can't even tell that this content has been replaced. I always had after seeing this result, I've started saying this in my lectures, that I think computer graphics people do machine learning better than machine learning people do that. Like, they just come up with such compelling applications that it really demonstrates the power. It is indeed magic. Here's another scene. You don't like the construction crane, replace it with trees, and so on, from another image. Okay, the image slicing is done manually. So a user defines what area you want to slice out. The filling in is done automatically. Okay, so a couple of quick things. What are some problems with instance-based learners or nearest neighbor learners? They are expensive. There's no real learning, and most of the work is done during test time. For each test sample, we have to search through all the data set, and this is slow. The other major problem is that it doesn't really work when you have a large number of irrelevant features. If you have if you have a small number of relevant features, like X1 and X2 are important, and then I have 10,000 random numbers in my feature set, my distances are going to get overwhelmed by these noisy dimensions, and I'm not going to be able to find nearest neighbors that are reliable. And ultimately, there's something known as perhaps a bit melodramatically, there is something known as the curse of dimensionality. It should really perhaps just be called the problem of dimensionality. We don't have to resort to hyperbolics, where distances become meaningless in high dimensional spaces. And I'll talk about that in a second. In particular, in image domain, nearest neighbors on images are almost never used. In fact, that's what made the work of Hayes and Efros so surprising, is that they were able to make it use. The reason why distances on images, nearest neighbor on images are almost never used is because these distances in pixel space are not very perceptually meaningful. And here's an example where this is an original image X. This is an altered X1, this is a shifted X2, this is a tinted X3. In this alteration, we've created box around this person. In shifted, we've just shifted the entire image, 1 pixel to the right. And in the tinted one, we've just added a color tint. All three of these images, by construction, because of the way we've constructed them, have identical distance from X1, X2, and X3 to X. But it's very clear that perceptually, these are three different images. We don't even notice the shift. 1 pixel shift is not going to make any difference perceptually, but because all the pixels have changed, you see a lot of distance. The tint you notice, but perhaps the most glaring thing if you want to recognize people is whether features are occluded. But from an algorithmic perspective, these are identical. And that tells you that the distances here are problematic. The key problem of curse of dimensionality, and this is why distances in high dimensional spaces, objects like images are never used, is that once you start moving from low dimensional spaces to high dimensional spaces, it takes a lot more data points to uniformly cover them. So this is a 1-dimensional space. Here are 4 points that are equidistant. This is a 2-dimensional space. Now we need 16 points with the same distance between them to uniformly cover the space. This is a 3-dimensional space. Now we need 64 points to uniformly cover the space. And when you don't have that amount of data, you leave large parts of the space uncovered, and so your nearest neighbor may be very far away from you and so on. So let's make this a bit more mathematically precise. And this will be the last thing that we discuss today. And after this, we will stop. But I think this example I find particularly valuable. Let's think about a sphere of radius 1 in d dimensions. What does that mean? What is a sphere of radius 1 in d dimensions? Well, in 1 dimensions, a sphere is just a line, right? This is our radius, this is r is 1. So a sphere is just this line in 1 dimensions. In 2 dimensions, a sphere is just a circle. We have a circle of unit radius r, and this is in 2 dimensions. In 3 dimensions, it's what we usually picture as a sphere, and there's some x, y, and z, and we have a sphere in some dimensions. And the question we're going to ask you to consider is, consider an outer epsilon shell in this sphere. Let me change the color so this is visible. So what I'm going to do is I'm going to draw an inner sphere of radius 1 minus epsilon. That's the radius of this thing. And that is an inner sphere. And we will ask ourselves, apologies for that. We will ask ourselves, what is the volume? What is the ratio of the shell volume versus the sphere volume? So there is some outer epsilon shell. So it is formed by the difference in the radius of 1 and the radius of 1 minus epsilon. And we will ask, what is the shell volume versus what is the sphere volume? In order to do this, we will need to know how do we compute volumes of spheres in d-dimensional spaces. And so, for a sphere of radius r, it's clear that when you are in 1 dimensions, the volume here is just 2r. It's just length of this line. When you are a circle, your volume is just area, right? So this is just pi r square. That's the volume. When you're in 3 dimensions, it's 4 over 3 pi r cube. That's the volume of a sphere in 3 dimensions. And this is my proof by ellipsis, also formally known as proof by induction. I claim that a volume in d dimensions of a sphere in d dimensions is it's r to the d. There's dth order dependence. I'm seeing an r to the 1, r to the 2, r to the 3. It has to be r to the d, and some constant factor k sub d. It doesn't really matter what the constant factor is. There's just it's proportional to r to the d. That's the volume of a sphere in d dimensions. And what I'm being asked is, what is the sphere volume? What is the shell volume divided by the sphere volume for a sphere of radius 1? So let's just compute, k to the d, 1 to the, apologies, there's typo here. Okay, so k to the d and 1 to the d, that's the volume of a sphere of radius 1 in d dimensions. And if I have to compute the shell volume, well, I just do 1 to the d minus k sub d, 1 minus epsilon. I do not know why this is giving me problems. Yeah. 1 minus epsilon to the d, right? So this is sphere volume minus inner sphere volume. That gives me the shell volume. And so this is the ratio. And it's pretty clear that, the constants cancel out. This gives me 1 minus epsilon to the d, because 1 to the power of d is just 1. And now let me ask the question, what do you think is the limit of this value as d goes to infinity? What happens as d goes to infinity? What happens as d goes to infinity is this 1 minus epsilon is a number that's less than 1. It is, epsilon is a small positive quantity. 1 minus epsilon is something like 0.99, if you want to imagine that. So it's a number that's less than 1. When you keep multiplying a number less than 1 by itself, this number starts approaching 0, which means the ratio is approaching 1. What does that mean? It means that if I ask you to imagine a sphere in d dimensions, and then I ask you what is the shell volume divided by the sphere volume, that ratio is 1. It means most of the volume of a sphere is in the outer shell. If I am the origin, most of the volume of the sphere is in that outer shell that is epsilon away. This is a problem. It's a very big problem. And turns out that, very quickly, epsilon being from 0 to 1, as d dimensions go from 1 to 20. So epsilon of 0.1, for example, already in 20 dimensions, most of the volume is, so this is the ratio that we were talking about. So already in 20 dimensions, asking for, the 0.1 epsilon, the ratio is nearly 1. This is a problem because if data is distributed uniformly in this space, then because most of the volume is in the outer shell, most of the data close to me is also in the outer shell. So imagine yourself as a data point. You are at origin, and you're trying to find out who is my nearest neighbor in this space, so I can copy the label of that nearest neighbor. If I imagine a sphere around me, because most of the volume of that sphere is concentrated in the outer epsilon shell, if data is distributed uniformly, most of the data points that I will find are also in that outer epsilon shell. It means that everything is a distance of 1 away, or it's constant distance away. All my nearest neighbors are living the same distance away because most of the volume around me is that far away, and data is distributed uniformly. This right here is why nearest neighbor methods fail when you have high dimensional data. We don't have good intuitions for high dimensional data, and all distances are become equivalent in high dimensional spaces. And the way to overcome this problem is to realize that data cannot be distributed uniformly in high dimensional spaces. If your data is distributed uniformly in high dimensional spaces, life is hopeless. But we can overcome this by not having data be distributed uniformly in high dimensional spaces. So with that, I'll stop. The summary here is we've introduced nearest neighbors. It's an image classification algorithm. It predicts labels based on the nearest training examples. The metric and K are hyperparameters. Don't fall asleep in talks, but if you do, you can ask about that. And the answer is always validation. So let's stop here. Next time, we will look at linear classification.